So we are going to start the amorphous form, crystalline form of carbon, which is fullerene. What is fullerene? As you have already studied in class 10th also about fullerene, it has a structure like football or soccer ball, you can say. First, we are going to see the preparation of fullerene. It is prepared, right with me. It is prepared by the heating of graphite in electric arc. An electric arc in the presence of inert gas. In the presence of inert gas such as helium or argon. When we heat graphite in the presence of inert gases, then so whenever we heat graphite in the presence of inert gases, it will be converted into fullerene. Okay. Most important features about fullerene is how many atoms are attached, what is the basically chemical formula. So the number of carbon atoms in fullerene is 60, is fixed, or we can say C60. Now in fullerene, the carbon atoms are arranged in closed cage like a structure. Closed cage like a structure such as football, you can say, or soccer ball. Therefore it is also called Buckminster Fullerene. Let me know when you are finished.
Done.
Very good. We are going to learn about the structure of fullerene. So another important feature about this structure is that the spherical form of fullerene is called buckyball. It is also called buckyball, and it consists of 26 membered ring. There are 6 membered ring, which is 20, and 12 5-membered ring. 12 5-membered ring and 60 vertices. That's it. Now it is very important to note that how they are arranged and how they are attached. So 6-membered ring are fused with either 5-membered or 6-membered ring. Six-membered ring. So basically, 6-membered ring can fuse with 6-membered ring, and Akifah.
Yes.
Okay. So basically, what I told you is that there are 6-membered ring, which is 20 in number, and there are 5-membered ring, which is 12 in number, and 60 vertices. So basically, 6-membered ring react with 6-membered ring can fused with 5-membered ring as well as 6-membered ring, but 5-membered ring fused with only 6-membered ring. Just right.
Done.
Very good. Now about its structure and hybridization, right? Each carbon is sp2 hybridized. That means one electron will be free from carbon and forms 3 sigma bond. 3 sigma bond. Again with other 3 carbons. Carbon has 4 electrons in its valence shell. This in Fullerene, one carbon connect with 3 other carbon with 3 sigma bond, and the 4th carbon will be free. 4th electron or delocalize. Basically, it will move in molecular orbital, which helps in conductance, molecular orbital, and show aromatic character also. Aromatic character. It has single as well as double bond. This fourth electron will basically form double bond with CC distance or bond length 143.5 picometer and 138.5 picometer respectively. That means this is for double bond and this is for single bond. Just right. And here all the properties, basically the form of carbon, allotropes of carbon is covered. Now we will start chemical properties, very less topics left. Then we will start chemical equilibrium. Let me know when you are done with this.
Done.
Very good. Now, write a topic, chemical properties of group 14. The first chemical properties is basically oxide of group 14. So basically from oxide of group 14, it forms two types of oxide. One is monoxide and the another is dioxide. And in monoxide, it forms carbon monoxide, silicon monoxide, germanium monoxide, tin monoxide, and lead monoxide. And dioxide CO2, SiO2, GeO2, SNO2, and PbO2. One thing which is very important to note that this SiO, it is formed only at high temperature. It is formed only at high temperature. Just write it. Are you done with this? Akifah?
Done.
Very good. Now, do you know how to calculate arrange acidic character? Just suppose order of acidic character. CO2, SiO2, GeO2, SnO2, PbO2. An inorganic compound or inorganic chemistry, how to calculate basically which one is a stronger acid and which one is weak acid? Do you know how to calculate? How to arrange? Yes or no, Akifah?
No.
Do you know how to calculate the oxidation state? Can you calculate the oxidation state of central atom?
No.
You don't know how to calculate oxidation state, right?
Yes.
First of all, you are going to take the which one is central atom? Can you recognize it? If I'm asking in CO2, which is central atom?
Carbon.
Carbon. So for central atom, we need to calculate the oxidation state of central atom. So I'm going to take it as X. Let the oxidation state of carbon is X. Oxygen is second most electron negative element. So it will gain electron, not donate electron, right?
Yes.
And how many electrons oxygen want to gain? How many electrons oxygen wants?
2.
2. So when an element gain electron, is it negative or positive? Charge on element on that element is negative or positive? If any element gains electron, the charge on that element will be negative or positive? Akifah, am I audible? Akifah? Akifah, am I audible? Akifah?
Yes.
Okay. So what I was telling you is that let the oxidation state of carbon is X and oxygen. If any elements gain electrons, then charge on that element is negative or positive?
If any element wants to.
If any elements gain electron, just suppose Cl plus 1 electron. If chlorine is gaining an electron, then charge on chlorine will be negative or positive?
Negative.
Negative. So you know that there are 2 oxygens, so I'm taking 2 here, and 1 oxygen will gain 2 electron, so I'm taking -2, right?
Yes.
And is there any charge on this CO2?
No.
No. So equals to 0. So x minus 4 will be 0 and x is equal to plus 4. So whenever you need to calculate the acidic, you need to arrange acidic character. First of all, you are going to calculate the oxidation state of central atom. Can you calculate in the same way as I calculated for CO2?
It will be 4 for all the
All that.
elements.
Now see the concept for acidic character. Acidic character. Oxidation state of central atom. OS stand for oxidation state, CS stand for central atom, directly proportional to acidic character. If any elements having highest oxidation state, positive oxidation state, that means that element or that compound is basically more acidic. But here you are seeing that all the central atom have same oxidation state. So if the central atom have same oxidation state, then go for size of non-metal inversely proportional to acidic character. Size of non-metal, or you can say electronegativity also. So you can see all the elements on all the central atom have same oxidation state in this compound, in these compounds. So we will go for size of non-metal. Now see which non-metal is so this is inversely proportional. That means carbon is the smallest one, so it is most acidic. So the acidic order will be like this. Okay,
Okay.
just write it.
Done.
Very good. Now we will go for halide. Halide of group 40. Now how many types of halides formed here? First is basically dihalide, and second is tetrahalide. Tetrahalide. That means EX4 for general formula EX2 here. Now you know that I already told you in oxidation state that tell me Pb plus 2 is more stable or Pb plus 4 is more stable?
Pb plus 2.
Plus 2. Down the group, lower oxidation state is more stable because of inert pair effect. So if I'm going to write Pb plus 2, Pb into x2, Pbx2 more stable than Pbx4, because in Pbx2 the oxidation state will be plus 2 and here it will be plus 4. Is that clear?
Yes.
This is more stable due to inert pair effect. Now, if we are going for order of stability in EX4 tetrahalide, order of stability GEX2 and GEX4. Since it is in middle, so basically GEX4 is more stable. In case of in plus, it is stable in plus 4 oxidation state than plus 2 oxidation state. Is that clear?
Yes.
Okay, just write it. Oh.
Done.
Very good. Now, write the topic condition for hydrolysis. Condition for hydrolysis. What is the condition? Write with me, then I will give an example. One bonded, we are going to hydrolyze or react a compound with water. One bonded atom should have vacant orbital. Whenever we talk about vacant orbital, that means whether it is vacant p or vacant d. Okay, and positive side, there should be positive side, that means there should be vacant orbital. Okay. Positive side, that means electron deficient. Also there should be less steric crowding around central atom. Just write it. There are two conditions basically for hydrolysis of compound. One is one bonded atom should have vacant orbital and one bonded should have and positive side, and there should be less steric crowding.
Done.
Done. Now we are going to hydrolyze CCl4 with H2O. Now you can see oxygen has lone pair and it can easily attack CCl4. Now come to CCl4 and check for vacant orbital. You know that carbon will have positive side and chlorine will have negative side, because chlorine is more electronegative than carbon. Is that clear?
Yes.
If carbon is making 4 bond, can you tell me, does carbon have any vacant orbital in this condition in CCl4? Yes or no?
No.
No. So if it is going to attack carbon, will it be able to attack on carbon? It won't be able, because carbon doesn't have any vacant orbital, so it will not be able to attack on carbon. And if you are going to see chlorine is basically third period element. This is third period element and it has 3d orbital, vacant orbital, right?
Yes.
But in case of chlorine, you are seeing that this is negative and this electron, this is lone pair electron, this is also negative. If it is going to attack CCl4, it won't be able to attack, because negative will repel each other. Is that clear?
Yes.
So in case of CCl4, hydrolysis is not possible. Is that clear?
Yes.
Now if we are going to talk about SiCl4 and going to hydrolyze SiCl4, just look at SiCl4 and think that chlorine is more electronegative, this is negative side and this is positive side. Now come to positive side, and since it is third period element, so it will have 3d orbital, vacant orbital. Okay.
Okay.
H2O will not attack on this chlorine because it will repel each other because of negative charge, but it can easily attack silicon because it have vacant orbital with the positive side, so it will form SiOH whole 4. Is that clear?
Yes.
Okay, just write it.
Done.
Okay, I'm going to write a point about it, the same which I have explained. CCl4, wait a minute, it's write with me. CCl4 is not hydrolyzed because carbon has no vacant d orbital, due to which it cannot expand its octet. It cannot expand its octet beyond 4. But SiCl4 is hydrolyzed because it can expand its octet by accepting electron pair as it has vacant d orbital. So basically, when we hydrolyze SiCl4, it will give SiOH whole 4 with 4HCl as byproduct.
Done.
Very good. Now, can PCl3 hydrolyze or not? SF6 can be hydrolyzed or not? Let me know, please. This can be hydrolyzed or not?
Yes.
Both can be hydrolyzed.
Yes.
But this is a wrong answer. The first one can hydrolyze because this is lone pair and fluorine is more electronegative, so it will have negative charge, and this will have positive charge, so it will attack this, and in the same way just this will form H3PO3 and HCl, and in the same way if you are going to see this will have lone pair, this will have positive site, but here comes steric crowding. The second condition for hydrolysis, steric crowding. I wrote it.
Yes.
Steric. Since fluorine is smaller in size, so the bond length will be smaller. And if you are going to talk about OH, if it will be hydrolyzed, just see. So this OH will basically, there will be repulsion. This is called basically steric crowding, and there will be, if there will be repulsion, it won't be stable. So SF6 is not hydrolyzed. SF6 is not hydrolyzed. Is that clear?
Yes.
So just write it, and here it comes to if you are done with this, let me know, please.
Done.
Very good. Wait a minute, please. And the chapter is over here. Okay.
Okay.
Chapter is completed. So we are going to start chemical equilibrium. Basically, equilibrium is a combination of equilibrium is a combination of two chapters, which is basically chemical equilibrium and ionic equilibrium. So first of all, we are going to learn about chemical equilibrium. So what is chemical equilibrium? Basically, equilibrium is a state in reaction. If we are talking about in physics, if we are talking in physics, that means just say anything is in equilibrium. That means from all direction, the force acting on this object are equal and cancel each other. That means it is in equilibrium. But in chemical equilibrium, it is like we talk in terms of rate of reaction. We talk in terms of rate of reaction. Forward rate of reaction is equal to backward of rate of reaction. So I'm going to define it. It is defined as, write with me. It is defined as point in reversible reaction at which rate of forward is equal to rate of backward. So basically we talk about reversible reaction. Reversible reaction, that means reactant is converting into product and product can also be converted into reactant. That is reversible. Irreversible is the one that is once reactant is converted into product, product cannot be converted into reactant. So equilibrium achieved in reversible reaction. And when we talk about equilibrium, chemical equilibrium, that means the rate of reaction, that means the rate of forward reaction is equal to rate of backward reaction. Is that clear?
Yes.
Write a note. It is dynamic equilibrium. Why we say dynamic equilibrium? Dynamic, basically in motion. That means it is in motion always. Rate of forward, this, that means this is going from here to here and this is going from right to left. That's why it is dynamic equilibrium. Dynamic equilibrium. Because reaction proceed with same rate in both direction. In both direction. Next point you can write. Concentration of, we are just talking about the characteristic of equilibrium, chemical equilibrium. Concentration of reactant and product do not change with time. Do not change with time. That means after sometimes the concentration of reactant and product should be constant at equilibrium. Are you writing with me?
Yes.
Very good. Next point, either mass, moles, intensity of color of reactant and product do not change with time after attaining equilibrium. after attaining equilibrium. This is my short form for equilibrium. Okay. If you are done with this, let me know.
Done.
So again, read all the characteristics that I have written here. Basically, equilibrium is the one chemical equilibrium in which rate of forward reaction is equal to rate of backward reaction. Okay, it is dynamic in nature. And what about concentration of reactant and product? At equilibrium, concentration of reactant and product are constant. Okay, and mass mole, if concentration are same, that means number of moles are same at equilibrium of reactant as well as product. Now you have to recognize which graphs are possible for equilibrium. Concentration versus time. First, the graph is about concentration versus time. The first graph is, can you recognize this is basically time and this is concentration. If I am giving you a graph is like this, can you recognize the line which represents reactant and which represents product? The line coming from upward to downward or the line coming from downward to upward, which line represents which? Reactant and product.
The downward to upward is reactant.
No, not at all. First thing, whenever there is reaction, we will have some reactant in advance that will react to give product, right? In initial at initial stage, if you are converting A into B, that means you will have something of A at T equals to 0, and here you can see the B moles of or molarity of B will be 0. After some time it will dissociate or something will happen and here will be something, right? So initially the product is 0 before reaction. Are you getting my point?
Yes.
Initially the product is 0, and so this is product, and initially we have something in reactant. So the from upward to downward is reactant. Is that clear?
Yes.
This is the first reaction. This is the first graph, and this is the concentration versus time for second. And this comes like this, and this comes like this, and they join together and go on a straight line. Okay, and the third graph comes out to be concentration versus time, and it is like this, and it goes straight. This is reactant, this is product, this is product, this is reactant. Which graphs are possible, or which graph is possible that which graph represents equilibrium? Just let me know. Can you tell me, or I should explain?
The middle one.
The middle one. So first, whenever there will be graphical question, you have to read first on which basis graph is given and between what is the relation. Basically, this is concentration versus time, right? And I am talking about at equilibrium. What I told you about concentration of reactant and product at equilibrium, I told you that concentration of reactant and product do not change with time at equilibrium. That means concentration of reactant and product is basically after attaining equilibrium are constant. Is that clear?
Yes.
Now, if you are going to see this, after some times, the product is going straight. That means product is constant. As well as after some time, the reactant is going on a straight line that parallel to x-axis. That means it is also constant. That means it is true for Equilibrium, isn't it?
Yes.
Now go for this. This is going, and after some time it is on a straight line. That means product is constant. And after some time you can see reactant is also on the same graph. So it will be also constant. So it is basically at equilibrium. So think about the next one. Okay.
It is also an equilibrium.
So what you told me this?
The last one is also an equilibrium.
Also at in equilibrium, because after some time it will be constant, right?
Yes.
Just write it.
Done.
Very good. Wait a minute. So I'm going to give you another 3 graphs in terms of rate. So read the passage of rate. So this is also the same graph, but the graph is between a rate and time, and the graph will be same. You know which one is reactant and which one is product, right?
Yes. What do we have to find?
We have to find which is true, which of this following graphs are or is true for equilibrium. Which graph represents equilibrium?
All are in equilibrium.
All are in equilibrium. This graph is in the relation rate versus time. And what I told you about, can you see this? This is for product, this is for reactant, this is for product, this is for reactant, right?
Yes.
Now, what I want to tell you is that rate of forward, we defined equilibrium in this term, rate of forward. That means RF is equal to rate of backward. In terms of rate, equilibrium is achieved when rate of forward is equal to rate of backward, right?
Yes.
Now, if you see rate of forward, this is basically forward. For forward, it is some, it is have some different value. So it is not true for equilibrium. Are you getting my point?
Yes.
And if you are going for this rate of forward has some other value than rate of backward. So it is also not true for equilibrium. And if you are going for this same rate of forward is equal to rate of backward, this is only this is true. So what I told you is that just read the characteristic of equilibrium. If we see in with respect to concentration of reactant and product, that should be constant. That can be equal, but constant is very important. The concentration of reactant and product should not be changed with respect to time. And when we talk in terms of rate of forward is equal to rate of backward. Equilibrium, what is equilibrium? Basically, if someone is going from left to right and right to left at the same time, that is equilibrium. Is that clear? Okay. Can I change the slide?
Yes.
Laws of mass action. Now see, laws of mass action. First, I'm going to write it. Write with me. It is very important and very easy. According to this law, rate of forward is directly proportional to molar concentration of each reacting species with raised to the power which must be equal to stoichiometric coefficient of reactants. Just write it, then I will derive and explain how it comes. Are you done with this?
Not yet.
Okay, let me know when you are done.
Done.
Very good. Now see, if you are reading it, you can easily understand that. According to this, rate of forward is directly proportional to molar concentration. That means molarity of each reacting species. Just suppose if I'm taking AA, small a is basically its coefficient, and BB react with each other to give CC plus DT. Okay, this is the reaction, and this double-headed arrow represents a reversible reaction. Is that clear? Now, if you are going to write a rate of forward reaction, that will be equal to for forward reaction. Forward, that means left to right, right? Is that clear?
Yes.
So this will be the reactant. So it will be a rate of forward reaction RF directly proportional to A raised to the power A. Whatever is the coefficient, it will come into its power, and B raised to the power B. So removing this proportionality sign, we have a constant that is called forward rate constant. That is called forward rate constant. This derivation is not important. The concept is important. Okay. Now, if we are going to write about backward, for backward reaction, C and D is reactant or not? Akifah, what I want to say, for backward reaction, that means right to left, C or D will be reactant or not.
Yes.
So backward reactant will be directly proportional, rate is directly proportional C raised to the power C, D raised to the power D. And for removing this proportionality sign, it will be KB into C raised to the power C and D raised to the power D. According to equilibrium characteristic, this is equation number 1 and this is equation number 2. Are you getting my point?
Yes.
And you know that at equilibrium, rate of forward is equal to rate of backward, right?
Yes.
So if we are going to put the value of RF, that is KF into A raised to the power A, B raised to the power B, will be equal to KB C raised to the power C, D raised to the power D, right?
Yes.
Now this value will be, I can also write KF upon KB will be equal to C raised to the power C and D raised to the power D upon A raised to the power A and B raised to the power B. Can I write it?
Yes.
And this forward rate constant, this is called forward rate constant, and this is called backward rate constant. This ratio is known as Kc. This Kc represents basically equilibrium constant. This Kc represents equilibrium constant, and Kc will be equal to whatever is the product we write in numerator with the power equals to its stoichiometric coefficient. This is the formula. And A raised to the power A and B raised to the power B. Is that clear, Akifah?
Yes.
So we don't need to derive all this formula. We need to apply. We need to know how to apply this formula. Are you there?
Yes.
Okay. So where from where you need to write? Here, right?
Yes.
Let me know when you are finished with this slide. I'll change the slide.
Okay.
Mm.
Can you scroll down?
Wait a minute. I forgot.
Done.
Very good. Now, this is basically how to write. If I'm going to give you this question and ask you, write the expression of Kc. So what you have to do is write the product side first, concentration of NH3, and whatever is the concentration, sorry, coefficient, it will be in power, and again come to denominator if this product is over and N2, and what its coefficient 1. So it's not necessary to write the power as 1, and the another is H2, so its power will be 3. Got it?
Yes.
Just write it.
Done.
Okay. So write the expression of Kc for this.
PCl raised to 3 into Cl raised to 2.
Okay. No, raised to not 2. It will be like this. What is the coefficient of Cl2? 1. What is the coefficient of PCl3? 1. What is the coefficient of PCl5? 1. Isn't it?
Okay.
Okay, just correct it. This is all in gaseous state. This is all in, yes. Write the expression for Kc.
H2 plus H2 into I2 over HI raised to 2.
Very good. Very good. Now, basically, this is equilibrium constant, and we have two types of equilibrium constant. Types of equilibrium constant. Two types of equilibrium constant. One is Kc and another is Kp. Kc is used when it is expressed in concentration term. So I'm writing if concentration of each reactant and product are expressed in mole per liter, then equilibrium constant is Kc. And if concentration of reactant and product are expressed in terms of partial pressure, then equilibrium constant is Kp. Is that clear?
Yes.
Write it. Are you done with this?
No.
Okay, let me know when you are done with this.
Done.
Very good. Now see, if I am going to write PCl5 in gaseous state, that is converted into PCl3 gaseous state plus Cl2 gaseous state. So if you are going to Kc, you know how to write Kc. What about Kp? Just see how we write. We write P and PCl3 in subscript, so that we can know that this is partial pressure of PCl3. In the same way, PCl2, and this is for PCl5. And if you are going to take about N2 plus 3H2 will give 2NH3. And if you are going to write the value of Kp expression, so it will be partial pressure of NH3 and raised to the power 2 upon partial pressure of N2 in subscript as well as H2 raised to the power 3. Got it?
Yes.
So in the next class, we will complete this chapter and then we will start ionic equilibrium or after that class. Most probably we will finish our chapter syllabus before your exams. Okay, we will have some extra class.
Done.
Okay, then we will continue in next class. Okay, do you have any doubt?
No.
Okay, thank you.